Hello everyone, welcome to the next lecture series. Myself, Professor Neha Sharma from Department of Computer Engineering, Kekewag Institute of Engineering Education and Research, Nashik. We are NAC-A accredited and NBA accredited for 8 branches. In this particular lecture series, we are studying one of the course from third year Computer Engineering 2015 course of Savitribai Phule Pune University, and the course that we are studying is Design and Analysis of Algorithms, which belongs to semester 2. Okay, so in this particular lecture, we are going to study the topic Huffman codes. So as it is our regular practice, before we start, let us have a look at the objectives and the outcomes of this particular e-lecture. So the objective of the lecture is to apply a greedy strategy to design Huffman code generation algorithm. And at the end of the lecture, we will be able to design the algorithm for Huffman code, analyze its complexity, and build the tree for Huffman code generation. Okay, so let us start now. So what is this Huffman code? As we know that it is a widely used compression technique. So it is a form of statistical coding. Now, whenever we are speaking about any encoding, so encoding basically means we have some data which we want to encode or compress it in some form. Okay. So there are a number of ways of encoding this data. You can encode it in using a kind of coding called as fixed length code, or you can encode it using variable length encoding. Okay. So basically, the sequence of bits or the number of bits used to represent each character while encoding is called as a code word. Okay. So in general, we can say that if we want to encode n bits, then it requires 2 raised to n characters. Okay. So this is a general statement about encoding. Now, when we speak about this Huffman codes, let us say that we want to encode a message composed of a string of characters. So as we know that codes used by computer system are nothing but ASCII code or Unicode. Okay. So ASCII, as we know that it uses 8 bits per character. So in the previous slide, we have seen that to encode n bits, we require 2 raised to n characters. So ASCII, it uses 8 bits, so it will require 2 raised to 8, that is nothing but 256 characters, right? Similarly, Unicode, it uses 16 bits per character, so obviously it is going to require 2 raised to 16 number of characters to encode. That is nothing but 65536 number of characters. So both these ASCII and Unicode, they are example of fixed length codes. Okay. So there is another variation of this which is called as variable length codes, right? Now, when we compare these two, okay, let us see this comparison with the help of one example. Okay, so let us say we want to encode a message that comprises of these symbols A, B, C, D, and E using fixed length code. So as we know that how many characters these are? 5. So can you use 2 bits to encode it? You cannot, because 2 raised to 2 is 4. Okay, so you cannot encode the fifth bit. Okay, so obviously you're going to require at least 3 bits. 2 bit is not enough because, okay, so if you have a message something like this, okay, and I want to encode this message, then how many bits it is going to require to encode? Yes, what we have to do is we have to count how many characters are there. So there are 12 characters, and for encoding each bit we require 3 bits. Okay, so number of characters is 12, so 12 into 3 is equal to the total number of digits that we require, or total number of bits required are 36. Okay, so what happens here with fixed length code is there is a lot of wastage of space. Okay, so how can we avoid this? The obvious solution that comes to our mind is using variable length codes. Okay, so what is this variable length code is? We will use less number of bits to represent more frequently used characters, and we will use more number of bits to represent less frequently used characters. Okay, so that is the solution. So the best way we can do this, or the best way we can implement these variable length codes, is nothing but Huffman codes. So this is what exactly we are going to study in this particular lecture. So how to generate this Huffman code and its algorithm with the help of example and its analysis, we are going to study now. So let us proceed for that. So Huffman code, it is nothing but it is a binary tree. So in this Huffman code generation tree, each leaf contains the symbol or the character that you want to encode. Okay, all the left branches or the left children are labeled with 0. Okay, all the right branches or the right side edges are labeled with 1. So what we have to do is, to generate Huffman code, we have to go from the root node till the child node and traverse the path, and what we get is nothing but the Huffman code. So this Huffman code particularly has a prefix property. Okay, what is the prefix property? Is no code is the prefix of another code. Okay, so we will see now how to generate this Huffman code. So the step 1 is, we have to create a leaf node for each character of the text. Okay, leaf node of a character contains the occurring frequency of that particular character, that is how many number of times it occurs. Then what is the next step? We have to arrange all the nodes in increasing order of their frequency table. Now here you have to note that the implementation of the Huffman code or the algorithm that we are going to design is, we are doing it using greedy strategy. Okay, now why we are using greedy strategy? What is the characteristic of greedy strategy? We want to get optimal solution, right? So we want to get the most efficient code. Okay. Second thing is, whenever you are implementing something using greedy strategy, we consider input in a particular order. It may be increasing order or decreasing order. So here in step 2, you can see that we have to arrange the nodes in increasing order of their frequencies. Okay, that is our next step. Then in the third step, what we have to do is, we have to consider the first two nodes having the minimum frequency. Okay, what we have to do with that? Now we have to create a new internal node, add their frequencies, that is add the frequency of the first two nodes. Okay, and whatever is the addition, whatever is the sum, we have to place in this internal node. So that is the next step. Okay, and then we have to make the first node as its left child and the other node as the right child. Don't worry, you will understand this when we see the example. As of now, I am just listing down the steps. Then what happens in the next step? In step 4, what we do is, we keep repeating this step iteratively until we consider all the nodes and we form the tree. Okay, so the tree finally obtained is nothing but our Huffman tree, from which we can generate the Huffman code. Okay, so this is in general the greedy algorithm for generating the Huffman code. There is a single parameter to this, which is C. Okay, so C is nothing but the total number of characters that we want to encode. Okay, now as you can see in this algorithm, um, we are using the functions min q. Okay, so that indicates we are implementing this Huffman code using min heap. Okay, so as we know that min heap is nothing but it is a priority queue. Okay, and the element at the root node is the minimum element if it is a min heap, and if it is a max heap, then element at the root will be the maximum element. Okay, so for implementing this Huffman code greedy algorithm, we are using a min heap. Okay, so first we are constructing a min heap with all the characters. Okay, then while uh, the length of the min heap is greater than 1, okay, so you have to continue this till we consider all the characters and we construct the tree. Okay, so as long as this condition is true, what we have to do is, The first step is we have to create a new node. Okay, so that is this step. Z is equal to new node. We are creating a new node. What we have to do with the new node is we have to add the first and the second element, that is first two minimum elements. We have to extract it from our min heap. Okay, and then whatever is the addition of its frequencies, we have to add it here in this internal node. So that is what exactly we are going to do. So using min q dot extract, we are going to extract the minimum element from the heap and add it to the left of the node, that is z dot left. Okay, we will extract the next minimum element and add it to the right side. Okay, and whatever is the frequency of this these two nodes, okay, we will add the frequencies and we will place it in z dot frequency. Okay, so this new node is nothing but it holds the frequency of addition of these two elements. Okay, so that is in z, and to the left of it is the first element with minimum frequency, and to the right of it is the next element with minimum frequency. Now what we have to do is we have formed this new node, so we have to simply insert it back into our min heap. Okay, so that is the next step. Min q dot insert. What we have to insert is we have to insert this node z. Okay, so we have to repeat this till our entire tree is generated. Okay, so at the end we have to return the uh, we have to return our min heap. So min q dot extract. So we have to return this entire heap. So from this heap, now once it is generated from our tree, once it is generated, we can easily find out the Huffman code. So we will see that now with the help of example. So let us say this is our example. We have these 6 characters and these are its frequencies. Okay. So as we know, using our algorithm, the first step is what we have to do in the first step is, so we have to first sort it in increasing order of frequencies. So in this first step, we have sorted it. So C with frequency of 5 comes first, then D, then E, then F, B, and A. Okay. Then what is the next step? We have to add the first two elements. Okay. And whatever is the addition of frequencies, we have to add it in the newly created internal node. Okay, and again insert it back into the min heap. So when you are inserting it into the min heap means what you are actually doing is you are inserting it at its proper position. So what will happen here, when you add this 10 and 5 it becomes 15. So when you compare 15 with these other 4 elements, okay, so the proper position of 15 will be here after 12. So that is exactly where it is getting inserted. Okay, then we repeat this step again. So what will happen in step 3? We will add E and F. So the frequencies is 11 and 12. So when you add this, it becomes 23. Okay, so when you compare 23 with 15, 20 and 42, you know that it will be inserted after B. So that is what exactly happens in the next step. That is our step 3, you can see here. So 23 gets inserted here. Okay, this goes to the left and this goes to the right. Okay, again when you repeat the step, what happens in step 4? This 15 and 20 will get added. Okay, so addition will be 35. Okay, so proper place for 35 will be after 23, right? So this 35 will get, this entire tree will get inserted here. Okay, again in last step what will happen now? In the next step what will happen? These two will get added. So addition will be 58, which is obviously greater than 42. So this internal node will get added here. And finally, in the last step, you will get the root node. Okay, so when you add 42 and 58, you will get addition of 100. So once you construct this entire tree, we have seen that all the left branches we have to label with 0. So as you can see here, this is labeled 0. Again here, all the left branches are labeled with 0 and all the right branches are labeled with 1. Okay, so our tree is now generated. So suppose I want to find out the Huffman code for A, it is 0. Okay, if I want to find out the Huffman code for D, okay, it will be 1 1 0 1. Okay, similarly, we want to find out Huffman code for E, it will be 1 0 0 and so on so forth. Okay, so this is how we generate the Huffman code. Now we have seen the algorithm for Huffman code, we have seen example of Huffman code. Now we will see about its complexity. So how do we analyze the algorithm for Huffman code? So as we know that for implementing this algorithm, we have used min heap, right? So min heap is implemented in the form of a queue. So when we perform any operation on this min heap, it will require total big O of log n time, right? Okay. And the initialization step of forming the queue or building the min heap, it will require big O of n time. Okay, that is what we know about the min heap implementation. Okay, so for initially for creation of the min heap, we will require big O of n time, and once the min heap is created, for every operation, okay, what operations we are performing? We are performing extract min operation every time, and at the end we are inserting the newly created internal node into the min heap, right? So for performing each such operations, we will require log n time. Okay, and total how many iterations are there? There are n minus 1 iterations. Okay, because those many elements you have to add inside the min heap. Okay, so what will be the complexity here? So obviously the total running time of the algorithm will be n into log n. Okay, why n into log n is there are n minus 1 iterations. Okay, building of the heap requires n time, and for every operation that you perform on the main heap, it will require log n time. So that is the reason total running time of the algorithm will be big O of log n. Okay, so that is nothing but about the complexity of the Huffman code, big O of n into log n. Okay, so we have studied um, in this particular lecture what is Huffman code. Okay, then we have seen what are the steps for implementing the Huffman code. After that, we have seen example, then algorithm of Huffman code generation, and finally we have seen how to analyze the complexity of that particular algorithm, and we have concluded that the complexity for this particular algorithm is big O of n into log n. Okay, so I hope you have understood the concept of Huffman code, and our objectives and outcomes for this particular lecture are fulfilled. So that is all from my side for this particular lecture. If still you have any doubts, you please feel free to contact on the mentioned email ID, that is njsharma@kkvad.edu.in. Thank you so much. We will end here.